So his work published at SDM 2011 conference. So SDM is a top data mining conference. To help you understand the contribution of Polonium, I'm going to briefly explain to you how traditionally malware detection works. So it's based on what we call signature-based detection. That means that security companies, say, for example, Symantec, they would collect malware sample from users, and then for each malware sample, they would generate a signature. And then they would distribute all these signatures to users. That's why every week you're probably getting several updates from Symantec. And then your computer will scan for files that match those signatures. But there's a problem with this approach, because it's not really good at dealing with what we call zero-day malware. That means malware that just came out. So for those malware, Symantec probably doesn't have a signature for them. So no samples, no signature, and no signature means no detection. So the key question here is how we can detect these malware, a zero-day malware, quickly. So Symantec developed a new approach, which is based on computing reputation of a file. So in this approach, Symantec would try to compute a reputation score for each application or executable file, say Microsoft Word.exe. So I'll tell you in a second how we would compute reputation score. But if we do have reputation score, then we can say for the files that have low reputation score, those would be malware. And Polonium is one way to compute these reputation score. So this is work that I have Symantec developed originally as an intern, first internship, and they were really happy with the results, so they brought me in for the second internship to help them fully deploy. So it's now deployed and used in all flagship Symantec's flagship Norton antivirus software. So it's now serving over 120 million people worldwide and it answered over trillions of queries of reputation. And in case you're curious about the name Polonium, so I squeezed my name into it. So there's Polo in the beginning, and also it describes the project, so it's meaningful. So it stands for Propagation Leverage of Network Influence Unearthed Malware. The key here is being network influence. So I'll explain to you why do we need it and what does it mean. So I'd like to quickly describe the data that Mellon worked with. So it works with over 60 terabytes of data collected from over 15 million machines that can anonymously report about their executable files. So each file is uniquely identified by its cryptographic hash. And there are over 900 million unique files total. And our goal here is very simple, to label malware and good files. So you may ask, why is it a hard problem? So there are three reasons. The first one is that we're now dealing with a really, really big data set, over 60 terabytes. And the second reason is that we want to detect not only some specific types of malware, but all types of malware that Symantec they are currently detecting. So that means we want a method that's really general, that's able to detect all these malware. And the third reason is that we want the false alarm rate to be really low. False alarm here meaning wrongly labeling a good file as a bad file. So you really don't want to label, for example, a Microsoft Word file as a bad file. So that will affect millions of customers. So we want the false alarm rate to be really low. So for all these three reasons, it's a hard problem. So how do we do that? So one approach is we can just consider these files and machines as separate identities. But my approach is, well, instead of doing that, we can consider the relationship between these files. So more formally, how I would view the problem is to turn it into a graph problem. So where I would build a bipartite graph. It's bipartite because there are two types of nodes, either files or machines. And I would add an edge between the file and the machine if the file appears on the machine. So after this transformation, we have a bipartite graph. And also after this transformation, we have over 37 billion edges, over 1 billion nodes, which are either machines or files. And we know some information about this graph now. Symantec actually knows some files are bad and some files are good. And also they have some idea about whether a machine is careful or careless. So careful machine could be a machine that probably have very few malware and always apply updates immediately. So there's some information that Symantec knows. And our goal here is still the same. So we want to find an unknown file. That means the files with question mark. And as I said, Symantec knows some information. And it's stored in what they call a ground truth database. So they know some unknown good, some unknown bad. And how we can use this information is say, well, if I know a file is a known good file in the ground truth database, then I can say, well, my prior knowledge or my prior probability about it being a good file, I can say it to a high number, high meaning like close to 1. So I can say, well, say close to 0. I mean, close to 1.9. And similarly, Symantec has an approximate idea about whether a file is good, a machine is good or not, or careful or not. And then, based on that, it can derive another number, say between 0 and 1, and that will represent the behavior or the trustworthiness of the machine. So this is computed based on our proprietary formula. So now the question is, well, given all these known information, how do we use them to compute the unknown information? Or in other words, how do we propagate the known information to the unknown information? And for that, I use a key idea called Gilbert association. So it's actually a very simple idea. It just means similar things are connected to each other. So in this case, what it means is good files are likely to connect to good machines, and bad files are likely to connect to bad machines. And in many fields, it's called homophily, similar, like-minded things are composed together. Or formally, I can show it as a 2x2 matrix. So these numbers are not exact numbers that Symantec is using, but the relative magnitude are. So the actual number values are learned from data. So what we are showing here is that for the rows, they represent the good file and bad file, and machines are the good and bad machine. So here you're just saying, well, that's a high string of association between good files and good machine, while a low string of association between good file and bad machine. So it's exactly describing the homophily idea that we were saying. So with this Gilbert association idea, then we can use it to propagate the known information to the unknown information. And to exactly do that, we adapt an algorithm called Beliet propagation. So it's a very powerful inference algorithm that's used successfully in many domains and many applications, say image processing, computer vision, best error correcting codes, and etc. So instead of going into details about how the equations work in the algorithm, I'm going to show you an example of how that works. So here I'm showing a toy graph of machines, 3 machines, and 4 files. So you can consider it as a dramatically scaled down version of the Polonium problem, which has millions and billions of machines and files. So here, my goal is to infer the reputation of file 2 and 3. Currently, their values are 0.5. So 0.5 means unbiased, so it's not either good or bad. And I have some known information about file and machine. So file 1 anyway is probably very good. File 4 is probably very bad. And machine A slightly good, machine B slightly bad, and machine C slightly bad as well. So how the algorithm work is that they would try to propagate these known information to the unknown. So the propagation can start either way, but suppose we start with the machines, then what the algorithm does, it would say, well, first the machine will propagate its reputation or its opinion about the things in this case files that are connected to it. So, for example, for this particular opinion that machine A is sending to file 2, it would say that, well, because machine A itself is good, and we use the homophily transformation or idea, then this opinion will represent the idea that machine A thinks file 2 is good because, well, it itself is good. So similarly, machine C would be saying, hey, file 3, you're probably bad because I'm bad. Okay, so that's how the propagation works. So after this propagation, all the files would collect each file would collect all the incoming opinion, and then we'll aggregate them, and then we'll update its reputation to a new value. So in this case, file 2 becomes slightly good, 3 becomes slightly bad. So that's one way of propagation from machines to file. So you would do it the other way around, from files to machine. And normally, we then update the file of the machine reputation, and then we get a new value. And so we would just do this iteratively until the reputation converges. So that's what the algorithm was done. And that's slightly more detailed. Slightly more detailed. So these are the only 2 equations that is used in the algorithm. So instead of going through the symbol one by one, I'm going to color code the equations and show you the examples that we previously seen. So the first equation is basically just saying that if you want to compute, say, the reputation of file 3, which is the left here, of Beliet formally, what we need is, we need my prior belief or prior knowledge about the file. In this case, it's 0.5 for this part. And then also my neighbor's opinion, the incoming opinion from my neighbor. And then I just multiply them all together, then I would get the new reputation about myself. So this is what the first equation does. And then the second equation, what it's telling us is how to compute a reputation. A message or an opinion. So that's the left part here. And what we need is we need the file's current reputation, which is this part from here. And then we do the transformation, the Gilbert association transformation here. Formally, it's called edge potential. So that means, well, if this is good, then we apply the transformation. Then the opinion would also be saying that, well, machine D should cover here. So this is what the equation is. So that means we know how to compute reputation. We also know how to compute the opinion. So then we know how to do the whole process of propagation and updating. So that's what the algorithms are. And we evaluated our method using real files, millions of them, and we used the standard tenfold cross-validation. That means we divided the ground truth files into 10 parts, using 9 parts for training or setting the prior reputation, and then evaluating using the remaining 1 part. So the chart here shows how well Polonium does. So the x-axis here is the false alarm rate, or false positive rate, meaning how many good files wrongly labeled as bad. So ideally we want it to be close to 0, no false alarm, that would be the best. And the x-axis here is a true positive rate. So how many bad files correctly identified as bad? So ideally we want it to be here. So no false alarm and every bad file is correctly identified. For Polonium, that's about 85% true positive rate and 1% false alarm rate. So it's very good. And even better is that when it's used with the many other technologies that Symantec is using to detect malware, it can boost those methods detection rate by 10 absolute points. So that's a really, really significant boost. And besides looking at the effectiveness, we also look at Polonium scalability. So running in a single machine, a 16-core machine with 256 gigabyte of RAM, you can see that the running time scale linearly with the number of edges in the graph. So here it's running, this point is running on the full graph of 37 billion edges. And for the smaller graph, it's roughly linear running time. So you may ask how we scale up Beliet propagation. So there are 3 key points that we exploit to make it fast and make it be able to run in a limited number of amount of RAM. So the first is that we observe that we actually don't need to run the algorithm till convergence. Because all we care in the end is whether the file reputation is above or below a threshold. Above the threshold, then it will be good. Below, then it's bad. So that means we can actually terminate the algorithm early. So that means faster algorithm. The second one is that we also observe, in terms of designing the data structure, we don't need to keep all the edges in memory. We can keep it on disk and then access those edges sequentially. So that alone saves up over 200 gigabytes of RAM. And thirdly, we observe that it's about part-type graph. So that means we don't need to compute all the messages in each iteration. We only need to compute half of the messages. So that makes the algorithm twice as fast. So this is for the single machine implementation. We have another paper in ICD, published in ICD 2011, which look at how we can scale up Beliet propagation using multiple machines or cluster machines using Hadoop. And this would be a very good case for when the graph does not fit in memory, which is actually the case today. So this chart here is showing how the time was scaled up with the number of machines. So the baseline is using 25 machines, and then we use 50, 75, and 100. So it's roughly linear, meaning for 100 machines, the time that it takes is roughly 4 times here. It's about 3.5 times as when you're using a 25 machine. So for this experiment, we did it on the Yahoo M45 cluster, which has over 400 machines. So that was Polonium. So that's one way to help analysts and Symantec to find malware. So those could be good starting points for them to look at the data.